Okay, so I want to remind you of a theorem that we had not too long ago, which had several equivalent notions that were related to seemingly different topics that turned out to be closely related. So let A be an n by n matrix. This one is already dead. Then the following are equivalent. So the first one that we had was that A is an invertible matrix, meaning that there is an A to the minus 1, an inverse matrix, such that their product is the identity. The second one was that the rank of A is n, where n is the size of the matrix. So this is only a square matrix, right? Okay. The third one was that A is row equivalent to the identity, meaning that if you do row operations, you don't just get a matrix with no zero rows. In fact, if you go all the way to the canonical one, you get the identity matrix. The fourth one was that for any vector B, any n-tuple B over whatever field you're working, AX equals B has a unique solution. Okay? And I think that these are the four that we wrote down so far. I want to add one that in fact we know this fact. I just neglected to mention it when we wrote this because it's really implicit inside this. So another way of saying, for example, that the rank is n, this means that it has no zero rows once you get to the echelon form. And remember that we had a statement that non-zero rows of matrix in echelon form are linearly independent, right? So another way of saying this, and by this theorem any of these, is that A, the rows of A are linearly independent. Linearly independent. Right? Do you agree that this is equivalent? And by the way, do you remember what the rank of A was equal to in terms of dimensions?
The dimension of n?
The dimension of n. What's the dimension of n? That doesn't compile. N is a number.
The dimension of A. Of the rows of n.
Right, the dimension of the row space. Remember that? Okay, so these, in fact, you can list 10 more here just saying the same things in various ways, but here's a new one. This is what I want to talk about in this, when we're discussing the determinant, and here it is, the determinant of A is non-zero. Okay, so once again, it seems like it's completely unrelated to the previous notions, to any of these. And in fact, it is, and we're going to prove it. Okay? So another way of checking that a matrix is invertible, check if the determinant is zero or not. Okay? And since all of these are equivalent, checking if the determinant is zero or not, you can check if the matrix is invertible. For example, by checking if the rank is n. Okay? So all of these are different ways of saying the same thing. It's pretty surprising. I mean, once you get into the notions and you see how they're very deeply intertwined and related, it stops being surprising. But at first, it seems like everything in this course is kind of related via this mysterious matrix business. Okay, so let's show this. Let's prove this fact for starters. It's not difficult. What I'm going to show is that 1 if and only if 6. And that would, of course, suffice because we already know that all the rest are equivalent. So I'm going to prove that 1 implies 6 and that 6 implies 1. Okay, so let's do that. Proof of, so let's start with 1 implies 6. So in this direction, we're assuming that A is an invertible matrix, and we want to prove that its determinant is not 0. So the first thing we're going to do is find the canonical, the reduced echelon form of A, denoted by C. So I take my matrix A and I start doing row operations until I eventually reach its canonical form, denoted by C for canonical. Okay? And if A is invertible, very good. If A is invertible, which is the assumption of 1, then by the parts of the theorem that we already know, it means that it's row equivalent to I, right? Then C is I. The canonical form is unique. If it's row equivalent to I, and I is in canonical form, then C is I. Do you agree? Okay. What is the determinant of C, therefore? Therefore, the determinant of C, which is the determinant of I in this case, what is I? Exactly. What is I? I is the matrix 1, 1, 1, 1, 1, along the main diagonal and 0 elsewhere. In particular, it's a matrix which we called triangular, whether upper or lower. And in particular, its determinant is the product of the diagonal entries. So the determinant of the identity matrix is always 1. Do you agree? Okay. And in particular, I'm going to write here something very surprising. It's not 0. Okay. So the determinant of the canonical matrix is not 0. And we've seen, that was one of the last things we did last time, that when you do row operations on a matrix, you may mess up the determinant. The determinant is not preserved under row operations. But if it's 0, then it's going to remain 0. Okay, and vice versa. So having a 0 determinant is an invariant of row operations. Okay, so A and C are row equivalent. That's how we got from A to C. So if the determinant of C is not 0, the determinant of A is not 0 as well. Okay, so let's write that. So the determinant of C is not 0, and therefore the determinant of A is not 0. It's not necessarily 1 anymore, but it's not 0, since A is row equivalent to C. Good? So if we start with an invertible matrix, its determinant is not 0. The other direction, 6 implies 1. I'm going to stick to the notation of denoting the canonical one, the canonical matrix of A, denoting it by C. And now we're assuming that the determinant of A is not 0. Okay? So if okay, so the way I'm gonna prove this, I want to remind you something, that if you want to prove some statement A implies some statement B, it's equivalent to proving that if B is not true, then A is not true. So I'm going to assume that 1 does not hold and show that 6 does not hold. That's equivalent, right? So if 1 does not hold, 1 was the assumption that A is invertible. So if 1 does not hold, if A is not invertible, I want to prove that not 6, that the determinant of A is 0. Okay? Everybody with me on the logic? This is crucial here. Okay? So I'm going to prove not 1 implies not 6. If A is not invertible, then, again, I'm going to rely on knowing the equivalence of the previous parts of the theorem. If it's not invertible, then its rank is not full, right? Then the rank of A is strictly less than n, right? Which implies, right, implies that in C, which is an echelon form, there's a 0 rows, not necessarily in A itself, right? Implies that C has a row, at least one, of zeros. Do you agree? What do we know of the determinant of a matrix that has a 0 row? 0. That was one of the little properties that we discussed last time. So therefore, the determinant of C is 0, because it has a row of zeros. And by the same argument that we used here, A is row equivalent to C, the determinant of C is 0, the determinant of A is 0 as well. Do you agree? Okay? And this completes the proof. If A is not invertible, the determinant of A is not 0. It's 0. Okay? So this completes the proof. Good? Okay? So this is not a complicated one. But you can see that we're using many facts that we've accumulated along the way. Okay? Things come in together. We didn't go to the basic definitions, but rather used facts that are not necessarily trivial, right? Some of these we had to work for. Okay. So this is this statement, and I want to write another theorem without proof and then some consequences. So here's another theorem. Maybe before that I'll write several, write a remark. Okay, I'll just say it. So the point is, let's go back to this theorem. Here's how you should think about this. Okay, look at this board, please. Here's how you should think about this theorem. You have 6 equivalent notions, and by the way, this is not the end. Well, it's the end of this board, but there are going to be more after we discuss some more notions. For example, later. Saying that these 6 statements are equivalent means that you have a lot of liberty here. If you want to check any one of them, you can check any other. Okay? So suppose, for example, you get a bunch of vectors, and you want to know if they're linearly independent or not. Okay? This theorem tells you, for example, you can take these vectors, straighten them out as rows in a matrix, and we already know what that really means. It means take their coefficient vectors and write them as rows of a matrix. And you want to know if they're linearly independent, right? That's what you were starting to check. If the vectors are linearly independent, that's if and only if their coefficient vectors are linearly independent. So for example, you can straighten them out as rows in a matrix and check if the determinant is 0 or not. If it's 0, they're linearly dependent. If it's not 0, they're linearly independent. Okay? So you have a lot of ways of approaching any question related to any of these notions via this equivalence. Okay, and that's how you should think about it. And in fact, this leads to many, for example, homework questions or exam questions have many seemingly completely different solutions, because en route, you want to answer one of these, you can check either one, whatever you feel more comfortable with checking, or whatever is easier in the context you're working on specifically. Okay, that's the way to treat this theorem, and you really have to remember these things. Okay, this theorem is really a major theorem, because we're going to go through the bridges of this equivalent many times. We're going to write an invertible matrix and say, aha, its determinant is not zero, and proceed from there. Or write a matrix for which we know that the rank is n, it has full rank, and say, aha, ax equals b has a unique solution for any b. Okay, and really go back and forth along these notions a lot. Okay, so this is one of the important theorems of this course. Okay, so now to a different theorem, which I'm not going to prove. The proof is a bit more technical. The determinant of a product equals the product of the determinants. Okay? This obviously requires proof. I'm not claiming at all that this is straightforward or obvious, even if you take examples. But you can verify it using one or two examples. Of course, only for n by n matrices. Okay, you can multiply matrices which are not necessarily n by n, and maybe the product will be n by n, but here we're only discussing n by n matrices. Okay? And here's a corollary of this theorem. If A is invertible, then the determinant of A inverse, A inverse exists, because that's what it means for a matrix to be invertible, is 1 over the determinant of A. Okay? And once again, this is not completely surprising. Things of this form you see in various places. Okay? Think, for example, where you see something similar in calculus. Think of functions rather than matrices, and think of something other than determinants. Something from calculus. But don't say it now. Just think. Okay, so I want to prove the corollary based on the theorem. Okay? So proof of the corollary based on the theorem. Okay? So A is invertible. That means that there is an A inverse, and of course the product of A and A inverse is the identity. That's the meaning of being invertible. Therefore, the determinant of A times A inverse is the determinant of the identity, which we already mentioned is 1. Do you agree? Okay. By this theorem, which we didn't prove, the determinant of A times A inverse is the determinant of A times the determinant of A inverse. Right? So this is by theorem above. By this theorem. Right? And therefore what? The determinant of A inverse is 1 over the determinant of A. Do you agree? Do I have to say anything more? I do. Right. I'm dividing by something here. I have to say, whoa. I'm not dividing by 0. How do I know that I'm not dividing? Very good. You're pointing over there. A is invertible. By the theorem with the 6 equivalent statements, its determinant is not 0. Right? So let's write it here. A is not 0 since A is invertible. Good? And this proves the corollary based on this theorem, which we didn't prove. Good? Okay. Okay. Yeah. So I think we're going to stop this one here, and I want to. We're not done with the determinant. It has a couple more applications that I want to present, but we'll do it in separate clips. So any questions? Any questions about these notions? Okay. So we know that the product of determinants is the determinant of the product. We know how to find the determinant of the inverse matrix. It's just 1 over the determinant of the matrix. And we have another little equivalent statement in this big TFAE theorem that we're gradually building throughout this course. Okay? Good. So let's stop this one here.